Welcome to Black Hat Briefings, held November 21st through the 22nd, 2001 in Amsterdam. This is videotape number 2B, a continuation.
The problem, and it was a bit subtle, the problem was the first 4 bytes of the second buffer may not be characters. There's a check which I had overseen, so basically that's the reason why it sometimes worked and sometimes didn't. I just have to put numbers there and then I can write to an arbitrary location. Okay, so as we have lots of stuff to go over in the second half, I'll not waste too much time on this. Well, here we are. I'll try to make this as short as possible. Here we are. We're in ball on C again. We enter 32 bytes, thus override the lowest order byte of the control structure with a null. Then we do not enter AAAA here. And then we enter some value here. And we enter some value to be written here. Properties of, there should have been a breakpoint, which is disabled. Okay. (9999) underscore 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 I. So if I hit enter now, we land in the small deallocator again. And there are a few special properties that apply here. Of course, the address where we write to should be paged. Underscore 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 is not paged. So I would like to supply a paged value here. I can't do that from the state user interface as I can't enter hexadecimal values in gets. So I'll just patch this in the memory. You all know that if you can't send hex data over network. You don't need to restrict yourself to ASCII. So something that's always paged in Windows NT in a single-threaded application is the address 7FFDE001. I'll explain later on why this is always paged because it's quite a funny thing. And then we just walk through this and get to this point. EDX points here. EBX is loaded with EDX plus 8. ECX is loaded with EDX plus 4. And then the value of EBX is written to the address pointed to at ECX plus 8. So again, we have an arbitrary memory override. It was just my stupidness that I didn't realize the first 4 bytes of the second buffer may not be characters. So I hope I have repaired my reputation, at least to a certain degree. But you see that these ones can be quite tricky, and another good argument for not using stress testing. All the EI guys are gone now, so I can bash them some more. All right. Moving on to the second half, exploitation reliability. We all know how annoying it is to try to own a computer and it just falls over, especially under NT where services are not automatically restarted and you just have one shot. It's really, really bad because well, your return addresses change with service packs, with hotfixes, and sometimes even with languages. So unless you know the exact service pack, hotfix number, and the language of the computer you're attacking, you're in for a bit of a gamble. And that is not exactly what you'd like to do. Secondly, in multi-threaded applications, you never know where your stack is at. So the standard Unix technique of jumping into the stack doesn't work at all. So you're jumping into some kind of shared library and try to find some code which locates your buffer and jumps into it. The problem with this is that those shared libraries can be relocated in memory and they can end up being pretty much anywhere. So we need to find some more reliable way to improve reliability. Now there is reliability at various levels. First off, there's reliability at the shellcode level. There's a lot of unstable shellcodes out there. I got hit by small bug pretty badly when I was starting out with shellcodes. Basically, I had an AMD computer, and that AMD computer was very Intel compatible. at least more Intel compatible as Intel's. Because I was writing a shellcode where I thought it was pretty sneaky to try to determine where I'm in memory by pushing to like 3 opcodes on the stack, namely pop EBP, pop EAX, jump EBP, and then issuing a call ESP. And that would give me my delta offset, like where I am in memory. And it worked fine on my computer, on my own box, just right. And then I tried to test it in the wild, of course, on the 200 Intel boxes which I have in my room. And well, I noticed that all of them crash. I couldn't figure out why. Now, after a lot of fiddling around and a lot of guessing, I finally started reading the errata of Intel. And Intel has documented that from the Pentium on, the call ESP instruction does not behave like the call ESP instruction used to behave. Basically, the call ESP instruction on the AMD and on the early Intels would behave in a way that it would first transfer the current stack pointer, no, it would first push the data, like I push the data, I'm speaking bullshit, I push the data personally. I issue the call ESP. Call ESP transform or moves the ESP value into EIP and then pushes the old EIP. That was the way it used to work, so my code would get executed immediately. I had pushed it before. Now with the Pentium on, they changed this. They first push EIP and then transfer that new EIP value, ESP value to EIP. Therefore, I was executing my own return address and that segfaulted. So you can get control reliably. If your shellcode is bad, then you'll be screwed. And there's a tremendous amount of bad shellcode around, like hard-coded addresses, especially for NT. Anyways, it's very much needed to have reliable exploits, whether you're a pen tester or a black hat or somebody writing a worm to celebrate the switch of the Internet Week. And therefore, I came up with a few funny tricks. First off, we all know and love format string bugs. I know this diagram looks a bit bizarre. Anybody here who's not familiar with how to exploit format string bugs, please raise your hand. Okay, then I'll demonstrate. Okay, this lame server is just a program listening on port 1999 and echoing back whatever I type using snprintf into a buffer and then sending it back. So if I send AAAA, it echoes back AAAA. If I send hello world, it echoes back hello world. Now, if I send hello world %LX, it sends back this because it's a format string bug. Now at this point, I can read out arbitrary data from the memory because basically for every argument, like for every format character, they start parsing upwards the stack from the pointer to the format string upwards into some arbitrary data there. Now, depending on how things are set up, if I have AAA and continue to pop off the stack and the AAA buffers on the stack, I will eventually get that printf pointer which is parsing the data into my own buffer, like right now. See the 41, 41, 41, 41? Now at this point, I am supplying data which I can display. And then there's the specification of printf. I'm not sure whether I have the exact specification here. Wait a second. Oh yeah. The ANSI ISO specification, the best $9 I ever spent. Apparently nobody else does this. Like nobody else spends, oh, wrong program. I think we should use Acrobat. Okay, and now we try to find printf. It should be in the library. I don't think this is going to be very intuitive. I think we'll look at another ANSI C specification. There is a format character called %n, which can be used for figuring out how many bytes a certain printf call has already written. For example, if you issue a %s, you don't know how many bytes you've written. Basically what you do is, the %n is not even listed in this one, or is it? Oh, here. Basically the %n tells the printf to copy the length of the string already written into the argument on the stack. So if I issue something like a printf %s %n string len, then len will be filled with the length of the string I've already written.
Address of length.
Sorry?
Address of length.
Well, whatever length.
So does it write to that parameter?
Yeah, it writes to the parameter there, to len. And we know that we can supply this parameter in case of a format string bug. So we can write the length of a string to an arbitrary location in memory, repeatedly. So, yeah, that's basically how it works. I think I should try to show it a bit. Okay, I'll explain later on what this little tool does. Right now it just displays memory at the location, says 7FFDE000. Whoops. And the data I'm going to send is going to look like this. We can see, is it readable from anywhere in the audience? Not at all. Okay, then I'll try to do it differently. We know that if we hit AAA here and then pop 12 bytes off the stack, that the next 4 bytes will be our value. We can pop those 12 bytes more elegantly by using .o1f, which pops 8 bytes, and %lx, %lx. Same result. Okay, now we know that we can write the length of the string we've already written to the location 41, 41, 41, 41. But just instead of issuing the last %lx, issuing a %n. So what I'll do now is, oops. Is this readable from the audience somewhere? It's AAAA, BBBB, blah, 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 and then %.01f, .08lx, and %08lx, and %n. So by changing this value here, we can change the length of the string which has been displayed. Because we can tell it to pad the lx to 22 characters, or to 55 characters, or to whatever you want. And then we issue the %n to write to the location here. And now what I'll do is I'll supply the location which is being displayed in that window. Okay, we'll save this. Okay. Now I know you'll not be able to see this in the back, but if I replace this 41, 41, 41, 41 with 7F FD E0 01, we should be writing a value to this location. See that? And now we can change the value we write by changing the padding here. Wait. From 55 to, let's say, 8. Well, 08. So we know that the padding of 08 will write the 23 hex value up there. So we can now write an arbitrary value there by just supplying the right padding. If we decrease this by 1, the byte we write decreases by 1 as well. Instead of 23, it's 22. Is this clear to everybody? Anything unclear? Raise your hand. At least you can ask that in Europe. It's frequently a problem in other countries where people, out of fear of loss of face, will not raise their hands if you ask something. So, okay. So everybody's more or less clear on what a format string does and why it does this. And format string bugs and heap overrides have the same thing, or have one thing in common. You write to arbitrary addresses and you write arbitrary values to arbitrary addresses. And the usual way to exploit these kind of bugs under Unix is you guess where your stack is at, where your return address on the stack is at, and you hijack the return address on the stack, or you override a value in the global offset table inside the executable and hijack one of the libc calls. Under NT, you can't do either, because first off, most NT compilers set the GOT equivalent under NT to be read-only. Now, if you write to it, there'll be a seg fault, nothing will happen. And secondly, if you try to guess where the stack is at, good luck. I mean, NT is inherently multi-threaded, and every process might end up in a completely different location with their stack, depending on server spec and so on. So Windows provides something called structured exception handling, which allows an application to handle its own exceptions, which is very useful, for example, if I first off want to hide sloppy programming, and secondly, very useful if I'm trying to, well, if I'm dealing with data I don't know and there might be an exception coming up and I just catch it and handle it. One might argue that the idea of exception handling is wrong in itself, as an exception should not occur, but then again. Anyways, there are two kinds of exception handlers under NT. There are a bit more now under XP, but I haven't played with them yet. First there's the unhandled exception filter, which is the last chance exception pretty much. If all other exception handlers have failed, the unhandled exception handler will get control. And when it gets control, well, it executes code. And there's an API call to install such an unhandled exception filter, which is called set unhandled exception filter. My desktop is getting chaotic. My computer is getting to be a bit of a chaos. So what we'll do is we'll look at the disassembly of set unhandled exception filter in kernel 32 DLL. Assuming I have it around. If not, I have it copied down somewhere. Okay, this is it. All it does is it takes its argument, the pointer to the filter, moves it into this location, and returns what was previously in that location. So anyone can see that the only thing we need to do to get control is write our value to this location and trigger an exception. Now the problem here is that we're dealing with the kernel 32 disassembly, and that's going to change from service pack to service pack, from hotfix to hotfix. But still, if you can determine the exact service pack number and the exact hotfix of a computer, this is the surefire way to get control with a heap override or with a format string bug. Just write the value in there, and boom, you're in. Okay. It's a bit boring though, and not very useful in the wild world, because when for the last time have you, or does anybody have a reliable service pack and hotfix fingerprinter over the network for NT? If you have one, gimme. the second kind of exception handlers which can be installed are per thread exception handlers. Every thread can install its own exception handler by manipulating a structure. This is all not very interesting. Okay. By manipulating the structure at fs.0. The structure at fs.0 is called thread environment block and is not really well documented by NT, but the Wine project has done a very good job at documenting it. And at fs.0, the first double word points to a structure of this format down here. It contains the pointer to the next structure of the next handler and the pointer to the handler code. Now, in order for a thread to install such a handler, you just issue the push offset of the handler, push the double word that's at fs.0, and then move your current ESP into fs.0. This will automatically create this structure here on the stack and will make sure that you don't erase any previously installed handlers. So basically, it creates a linked list of these structures which contain a handler. And when an exception occurs, NT calls the topmost handler, like the handler that was last installed. If that handler claims it fails, it returns with an error value, and NT calls the next handler. And so on, that goes down all the way until eventually no more handlers are left and the unhandled exception filter is called. So I knew about this for quite some time from the old copy protection days, because it can be used very efficiently for funny anti-debugging, like setting the computer into single-step mode and catching its own exception, and if somebody single-steps it in soft ice, then nothing will happen, and your program knows somebody's single-stepping it. It's not very, very hard to crack, but it can be used for a lot of funny games, until I finally had the idea that it's a good way to get control. We overwrite a thread's exception handler and trigger an exception. Should get us control. Now that was a simple idea. It turned out to be a bit more complicated in practice, but still it's quite useful. I mentioned fs.0 forms a linked list of these structures. We go through all this, the entire chain of handlers, and if we can override the value at fs.0 and we can make it point to a structure we have supplied, then we're in. Of course we have to trigger an exception afterwards, but triggering an exception is not always a hard thing to do. Now, we have a few problems here. The structure we're trying to override is at fs.0. And as you might remember, I don't think there's any way in the world where we can do cross-segment arbitrary data overrides. Neither with format string bugs nor with malloc bugs we can do a cross-segment write. We need to write to fs.0. We're screwed. We can't do it. Okay. What nobody seems to have tried to document before is that those thread environment blocks are created at highly predictable addresses. Now they are not only at fs.0, but they're mapped into the address space of the thread as well. Officially, a program is not allowed to use it, but they're there, and they can be accessed. And I wrote a small test program to show how TEBs are actually allocated. And the results are that the first thread always is at 7FFDE0000, the first TEB for the first thread. And then for the second thread, one page below, and so on, up until to the 11th thread. And that is at 7FFD4000. And the 12th thread starts at 7FFAF00, the 12th TEB. And from then on, it goes on to infinity. I quit testing this at more than 500 threads and just goes sequentially down from there. So we know we can predict where the TEBs are going to be. That's why I knew that 7FFDE001 would always be paged. So we know that we have a bunch of pages that are always going to be paged. And we know that if we write to these and create a structure in these pages that are always paged, we can get control. We're facing a few difficulties though. I hope this slide works. If not, I'll show it live. You have threads 1 to 4, which have been sequentially created. Now, thread 2 finishes and exits. And this region here becomes non-paged. So if we now start to sequentially override those TEB structure beginnings, we're going to get a segfault with the second thread. And assuming that we want to exploit with the fourth thread, we're never going to reach it because it's segfaults before. So we have to somehow deal with the fragmentation of the TEB table. I don't know what this slide was all about. It was supposed to be very visual for something, but all I can see is typographical errors. Oh yeah, well, it shows a bit more how the TEB might become fragmented. I think I'll rather show that live somehow, if I manage to get back to my TEB view. Okay, TEB view displays the first 50 threads TEBs, like the data there. I whipped this up yesterday. I want to make things a bit more visual because I noticed that nobody is capable of reading the soft eye screen in the audience. Now I have a client that simulates true traffic to a certain degree. It connects to the server, lingers for a while, disconnects, and does all this with varying degrees of delay. So you can see a bunch of threads being created and connecting. And now you can just watch how the TEB starts. Well, it's not really fragmented right now because there's continually new threads being created. But once there's a bunch of threads which all die at a certain point and no new threads coming in for a second, it's going to be heavily fragmented. Now you can see here that we have a bunch of threads running. Now the TEB is very heavily fragmented, for example. That's not going to be easy to overwrite them sequentially. So hello, back to PowerPoint. Any questions concerning this so far? I forgot to ask. No? Right. Okay, I mentioned those difficulties before. We don't know with which thread we're working with. I mean, we just connected. We don't have the thread number or where the TEB is at. And the TEB table may be fragmented, so we have no clue where to write to. So we need to exploit in a certain strategy. What I do usually is I create a large number of threads. I create a heavy load on the server. Because if I create a heavy load on the server, I have a good chance that one of my threads will be amongst the first few, way up there. If you look at the TEB again, darn, should start learning GUI programming more in depth. Okay, if I create a heavy load for quite some while with my threads, I can assume that at one point one of my threads will get like one of the TEBs high up on that list. I want my exploiting thread to be as high up on that list as possible because I want to get control, and if I am overriding sequentially from the beginning, then I'm not going to get very far if my exploiting thread is somewhere down the list. So I create a heavy load on the server to get one of my threads actually populate the first region. I let all of them die quickly. And then I connect, and when all of them die quickly, this TEB table is very fragmented. But a few places very high on the list are going to be free. So I connect with my exploiting thread, which is going to be high on the list. And the next thing I do is I connect with a lot of junk threads to just fill in the gaps in the TEB table. And then I start exploiting. Unfortunately, there's no way to visualize it. And the result of this is that you have a reliability of 80 to 90% of exploitation under multi-threaded systems. And this is without knowing whether it's NT2k or XP, without knowing the service pack, the language, or anything. Now, officially, the speech would be at its end from the slides, but I'll demonstrate a bit more. Trying to figure out where I have an empty command shell. Okay. We'll quit the lame client now, and I'll demonstrate how we actually can overwrite the TEB parts. Wait a second. So we can assume that my lane server, my lame client is creating quite some traffic here. So he's doing the job of creating, he's doing the job of creating a lot of threads. Of course, in a true environment, there would be more than just one client here, but I let all those threads that are creating traffic die. And then, wait, I'm connecting with my exploiting thread. Of course, in reality, this has to happen really, really fast. Just to make it more visual, this is, okay, cd, like at speech. Okay, and I create a bunch of threads to fill in the gaps. I don't need those threads right now because there are no gaps, because all traffic that was there was generated by me. But actually, I could run 2 instances of lame client. That should work. I'll try to visualize it this way. Wait a second. Okay, the application crashed. Let's get back to the lame server. And then we start up TEB view. Process ID has changed to 3205. Okay. We minimize the lame server. I'll quit any applications we don't need to get an unschool result. Okay. We start one instance of lame client. We start another instance of lame client to create a heavy load. I prepare for connecting with the exploiting thread. I let one of my lame clients die. I hope I've gotten one of the threads high above, I'm not sure. I have one of those, I'm still alive with my thread. Oh, I'm trying, now I'll create a bunch of threads to actually fill in any gaps that might be there. Now I can be quite, this was wrong. I should have executed exploit 2. Ha. Dope. I told you this was not going to be easy to visualize. Lame server is waiting. Lame client should be starting to generate traffic. I have 2 instances of lame client running. I'll try to figure out what the PID of the lame server is in order to be able to see what the TEBs are. Okay, here we have the TEBs under fairly heavy load. I ready myself to connect with the exploiting thread, and I ready the correct program in the other window. Okay. Now I make sure that if I just flip this, the right window will pop up. This should be it. Okay. I let one of the lame clients die, and I mistyped. Okay, I start up the lame client again. Well, this all happens in the in a fraction of a second if you have written it in an exploit, but just trying to visualize it is a major pain. Okay. Sorry? Exploit 2. Thanks. Okay, wish me luck. Flipping it gets me to the right point. I let one lame client die. I connect. I've probably gotten the third one from above. Actually, we can verify that I've gotten one up on the list by letting the second lame client die. Okay, we let this die, and we can see that I've gotten nothing. Oh, yeah, I hit the up arrow. Okay. Well, at least I'm filling the time. It's quite hard to just hit enter. Okay. We let, okay, I just have to hit enter then. No hand on the up arrow. I let one client die and connect, and now I let the second lame client die, and you can see we've gotten a thread way up on the list. Is this at least plausible? Okay, now as we've gotten a thread way up on the list, we start the lame client again to simulate real traffic. And our exploiting, now we create a bunch of threads to prevent there being a fragmentation directly before our thread, exploit 2. Thanks. And we just hope that there will be no fragmentation now before our original thread, because we'll start exploiting now with the original thread. And I'd love to demonstrate how I write to that address, but if you can tell me how I write 7FFDC000 or 001 using the standard interface with my regular keyboard without a number pad, you're my king. So, yeah, but I don't have a number pad, so I'll try. Function key. And then, oh wait, now I have a number pad apparently. And now we have to guess, oh no, the first value we want to write is 01. Let's hope this works. 01. Shouldn't the cursor be advancing? 001. Oh, this was not good. 01, no. 001. I don't know whether that's the right character, but let's hope. Okay, that's the 01. The next one would be E0. E0, we'll just convert it. The best application Microsoft has ever written. No, I'm just kidding. I'm seeing Rooster back in the room here, and I had to make stupid jokes about Microsoft. So, no, it's not E0, it's D0, which we want. D0, which is 208. Alt func 208. And then it's FD. (253). No, it's only 7F, which should be 127 or something. 127, yeah. 127. It's the backspace character. So we're screwed. But it's possible. We just can't do it on the keyboard here.
Just a small Perl script that echoes.
Yeah, we could do that, but right now I have this small thread here in the very beginning. Well, we've seen that once we have the thread, we can write to arbitrary addresses. And I've demonstrated that we can now sequentially overwrite those exception handlers without problem. Do you believe me that this works? Okay, then everything's fine. Shut up, Rooster. Okay, any questions concerning this? How much time do we have left? 45 minutes?
Half an hour.
Okay. So somebody please come up with questions while I come up with something. Yes?
Yes, where are you from?
Germany.
Thank you. Another question. You talked about format strings bugs.
Yeah?
I really, if you have the time
Yeah?
and the audience is interested, I would like to have a little bit more detailed information about to find format string bugs and
Okay.
to exploit it, because I saw the demo and it looked fine, but I really didn't get the source code thing in my mind working really.
Okay.
You understand?
Yeah? Okay.
Learn me string.
Explain a bit more about format string bugs. Are there any? We can do that in a minute, yeah? I mean, we still have time apparently. Any questions concerning this multi-threaded exploitation crap? Nothing? All right, then we'll start playing with format string bugs some more. Yeah?
I have a question, just maybe a little bit off topic, but do you know if there's anything similar to exception handlers in the Unix world?
Good question. It's not standardized Unix. I would bet Sun has implemented something like it, because they are the direct competitors to Microsoft. But are they actually implemented in a similar way? Because the Windows exception handlers are not like the standard exception handlers in C++. They're implemented using try-except macros.
I mean, you have something like a signal handler for seg-b will be the new.
Yeah, the signal handlers would be the next best thing to an exception handler. But signal handlers only get one exception, while an exception handler gets any exception. And I think there are very few applications explicitly installing a segfault handler. So signal handlers are not quite as useful as structured exception handlers when it comes to exploitation. I'm not aware of anything right from the top of my head. And I don't think that there's anything that's in the standard besides the C++ exception handling with throw and catch. Okay, so let's play with format strings some more. We'll quit this crap in the background. Oh, wait a second. Oh yeah, actually works. So I think, if nobody minds, I'll explain a bit more how format string bugs look in the source, how they can be found in the binary. Unfortunately, I don't have the nice example of having format string bugs in Checkpoint anymore. I don't have Checkpoint installed. But we can play a bit with that. Whoa. Hello? Not that I know. Okay. Okay. Actually, this lame server is a pretty good example for playing with format string bugs. The site exec bug in WooFTP was similar. You could see your own echo, so you could, even if you didn't know what machine you were running on, you could just try to exploit it. A friend of mine spent about a week just sending weird format characters to some weird IRIX box he had found somewhere, trying to figure out how this one could be exploited. Not that any of my friends engage in illegal activities. What? I don't know any. If they do, they must do it without telling me. Rooster, would you consider yourself my friend? Okay. Now I think we'll have a small look at the source of that lame server. The mistake is pretty much here. It's called argument deficiency. Actually, I have an entire chapter on that in the other presentation. Let's try whether we can find it. Okay. Now this is the speech I used to hold back in the days, last time. Okay. Format string vulnerabilities basically come from the fact that programmers are too lazy to type the full statement. And I think any one of us, when he writes a small test program, feels inclined to write printf stuff instead of printf double quote, %s, double quote, colon, semicolon, whatever it is, comma, stuff. So programmers are lazy, they do a printf user data. All programmers are stupid and don't know the specification and think that syslog doesn't accept format strings and passes straight value. So basically, format string vulnerabilities or format string bugs can be classified as argument deficiency bugs. People are lacking an argument here. A correct printf call has two arguments, one format string with a format character and one piece of data being expanded. The printf user data doesn't. So we have an argument deficiency. We went over exploitation details. We'll play a bit more with that later on. Basically, all format strings can be classified like this. So if you see a printf and the format string is not enclosed in double quotes, and it has an argument deficiency, you should look very closely. The same goes for binaries, actually. I can show you a disassembly of Microsoft's FTP server, which has a format string bug. Unfortunately, a part of the code that is never reached. Never ever. Unless you take a hex editor and toggle some flags. Yeah, I know that joke takes some time. Okay. I'll erase this comment here. Okay. The pu debug print function is a debugging, printing, or debug messaging function which uses VSN printf later on to actually implement something like a sprintf. So the programmer issue a pu debug printf and therefore can put out error messages kind of like printf, which is probably very handy. And I have written a small script to automatically detect these format string bugs. The funny thing is, in non-optimized code, if something was compiled with not the highest optimization settings, you usually have something after a call which is called stack correction. All the arguments were pushed onto the stack, and then the call was issued, and afterwards the stack has to be corrected again because all the arguments to that function are still on the stack, wasting space. So you have something after the call which is called stack correction here. They add the amount of arguments times 4 for the size of the arguments to the ESP. So you can see an argument efficiency in the disassembly by looking at the stack correction. And then you can check whether the format string is enclosed in double quotes or whether it's dynamic, and therefore find these buggers. So we have a total of 212 calls to pu debug print. Now we have two alternatives. We either go through each one and look, which I won't do. Or we write ourselves a script which does all the checking for us. Now to start with some shameless self-advertisement, I'm holding a class on this entire binding auditing crap at Black Hat usually. So if you want to learn more about it, contact me and I'll gladly teach you. I have to pay my rent somehow. So the IDA disassembler is scriptable. You can perform boring tasks automatically. So I have created a script that takes two inputs. First off, the address of the function that we're dealing with. Secondly, well, it takes three inputs. Secondly, the amount of stack correction it needs to have, like it should have as a minimum. For sprintf, that would be 12. For printf, that would be 8, because we need at least 2 arguments for printf or 3 for sprintf. And then then it checks whether the string length of the format string is longer than 1. It gets confused by a simple printf \n because that's only one character, but well, I never claimed to write bug-free code. I'll just run this, and if this is confusing you right now and not really helping you out with understanding format strings better, don't worry. We still got time for that later. Okay, I'm running this script. The address of the function we're investigating. Oh, I forgot to figure out the minimum stack correction. This was not good. So we have to calculate the minimum stack correction. We have 3 arguments in this format string, and we only need 1. So the stack correction of 1C hex 28 is 8 bytes larger than what we need. We need a stack correction of 20 because we only need 1 format character, and there's 3 in this format string here. So the correct stack correction would be 20. And it was the 4th argument, which was the format string, if I remember correctly. If I'm wrong now, we'll notice in a second. We let the script run. And it hasn't found anything, so I made a mistake with the number of the format string. 1, 2, 3, 4. Yes, this is true. Hold on for a second. Never try to present something you haven't tested. It'll work in a minute. I think you're used to me fumbling up now, so. Last try. Oh, yeah, here we go. It has successfully detected an addition to ESP with an argument efficiency, 16, and a dynamic format string. Argument 4 is not enclosed in double quotes. It's temp buff actually here. Temp buff is created before using a double sprint, like a wsprintf. So they create this debug string command too long, partial %d bytes, now %d, blah, 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 from host %s. That from host is actually looked up through a DNS query. So if we were to enable debug flags in this Microsoft FTP server, which is not enabled by default, or which is a bit tricky to enable, and we would then spoof or write or run a rogue DNS server and connect and send a too long string to that FTP server, Microsoft would catch it and have us get in there via a format string bug. Rooster, do you know any FTP servers in the Microsoft network running on debug mode? Okay, thanks. This just to introduce you to the topic of binary auditing because it's one of my stranger hobbies. Anyways, enough confusion. I was just trying to show you that these things can be found automatically in the binary. I think you'll want to go back to some of the actual playing with format string bugs. Now, we showed before that we send this string here and pop from the stack. We eventually get to our own data. Does everybody understand why this is the case? This is the case because the buffer lame2, which is the buffer supplied by the user, is on the stack. So it's clear now why we're reading out 3 values before we actually reach our own data. We read out the return value, then sock, then blah, and then our data. Because we're reading upwards from here, basically. So we eventually reach this. And we can now read out arbitrary data by, for example, this was segfault now, but this is, we'll try to read the string at address 41414141. That's pretty clear. We can now read arbitrary data. There's no data at 41414141, but doesn't really matter. We can supply other values here. We can write to arbitrary addresses using %n. We've shown that before as well. And if push comes to shove and we don't have anything used to write to, we can still do something like %20,000s and smash just about any buffer if they're not using snprintf. So there's a whole lot of things we can do once we have a format string bug. Actually, I'm using sprintf here, so we can actually try to smash the buffer. The target buffer is 5,000 bytes long. So we'll try this. I don't know whether actually that libc will handle values as large as 6,000, but we'll see. And I think the server has just died. Yeah. So format string bugs really are fun to play with. Unfortunately, they've gone away far too quickly. I mean, the NSA predicted 20 years ago that buffer overruns wouldn't be around for much longer. But buffer overruns are so elusive in nature that they can still be found pretty much anywhere. Just go and audit Apache. The modules are insanely bad, and one would think that Apache is pretty secure. And format string bugs can be found automatically, so the hunters don't have to go out there hunting big animals and being afraid of being lost in the code woods, but they just send their little script out there, does all the hunting, and ramasses all the funny little animals, and they're gone. Up until the next bug class comes out. Any more questions concerning the format string bugs? Okay. Any other? Yes?
Have you seen any working format string exploits for Windows?
Yeah?
Yeah.
You mean for in the wild applications?
Yeah.
I gave Checkpoint a working one for their administrative client. I haven't seen any of them published, but there's about 5 people writing NT exploits, and 2 of them are Japanese and don't speak English. And there are a few more writing NT exploits actually, but they're not very good at it, it seems. Most of the NT shellcode you see, most of the NT exploits you see are very, very bad. People don't, like, just creating an exploit for their own lab, just testing it there, or using EI's IIS exploits or whatever. So the NT exploit writing scene is very, very small compared to the Unix exploit writing scene. And to be honest, not like, outside of government organizations, I know about 3 people looking at binaries, and you don't find format string bugs with stress testing usually, so you don't have too many of them on a Windows anyways. Another thing that's going on a Windows is that you don't have syslog. Syslog is a famous source of format string bugs. You have something called format message and then send message and so on. No, not send message, but format message, which is not exploitable for format string bugs. So the amount of, I have to be honest, I've never seen a format string bug in an application specifically written for NT. I've seen format string bugs in applications ported from other platforms. Checkpoint was not explicitly written for NT, but you had Unix programmers. And my explanation was for this was that most Windows programmers have never heard that something like vsprintf exists. I mean, they're too busy using MFC. Any other questions? Okay, then I apologize for not having enough stuff to fill the second half completely, but I think the stuff I presented should make for some nice experimentation at home. And I thank you for being here. Have a good day.